All right, we're going to go ahead and start the talk for today. So thank you all for attending. Today's webinar topic is Geophysical Methods for Assessment of Embankment Dams. It is February 23rd, 2020, and I am Ryan North, the Principal Geophysicist here at Olson Engineering, who will be walking you through this webinar. And then please save all your questions for the end, but as we get closer to the end, you can start posting all of them in the comments. And then Sterling, who is co-hosting with me, will then make sure that I address all of the questions that have come in or comments at the end. And we'll be here as long as there are still people who have questions. All right. All right, so the outline of today's talk, generally, we're going to talk about what is an embankment dam, what are some potential failure mechanisms for embankment dams, what are some of the targets of interest, what geophysical methods are applicable to these targets, and then we have 2 case studies at the end. All right, so what is an embankment dam? Well, it's a man-made dam, and we're ignoring the beavers who may make a dam because they generally don't make it out of earth materials. And it's generally, an embankment dam is created by placing and compacting a mix of semi-plastic, various materials such as soil, sand, clay, or rock. There is generally a semi-pervious, waterproof natural covering for the surface. And then generally there is a dense impervious core, typically clay. The materials are fragmented independent material particles, and then friction of the particles binds them together into a stable mass rather than using a cementing substance. So here's a cartoon sketch of an embankment dam as it is generally designed. It's generally somewhere around a 1-on-3 slope on the sides. We can see that we generally would excavate down to rock. If we were building one from scratch, we would fill in the core area of the dam with clay. We would use semi-pervious materials for the bulk of the surface of the dam. And then we would put on top of the semi-pervious materials a rock toe and riprap protection to reduce surface wear on those areas. And then quite often the top surface is also covered as well. And again, these are how a dam should be designed. Unfortunately, many dams predate having rigorous standard design and construction of them, and they've been absorbed by their owners as is. So here is another cartoon sketch of a dam from a view above it, downstream. And we can see the right side, the left side, which are defined as going downstream. So then there's the upstream slope, the downstream slope. We have a conduit where it's designed for water to go through to control the elevation of the water on the upstream side. And we see benches and the slopes. And then we also have a control area because we want water to flow over through, as seen in here, the emergency spillway if the water level approaches the maximum height of the dam instead of overtopping over the dam. So here's another sketch. Again, most of the same stuff as the last time. This is from FEMA. And it shows the different components of a dam. Now, I'm also going to mention here on this one slide, a levee. A levee is not the same as a dam, but it shares many similarities with a dam. And also, a lot of the methods that we'll talk about later are applicable to the levee in the same way they are in the dam. So a levee can be called a levee, a dike, an embankment, flood bank, or stop bank. They are similar to embankment dams. They are typically shorter in height relative to the surrounding landscape and much longer. They're typically elongated, naturally occurring ridges or artificially constructed wall that regulates water levels. And they're usually earthen and parallel to the course of a river in its floodplain. Again, these are generalities. They're not always true. All right, so one thing I put in here is who owns most dams and levees. The reason I put this in here is because ownership is sort of tied to some of the geophysics later, in the sense that the federal government, for example, the Army Corps of Engineers and the Bureau of Reclamation, may control dams, but they may not actually own all of them. They may own some. State governments may own some, and local governments and private individuals. But the big takeaway is that nearly 85% of levees and a large number of dams are actually locally owned and maintained. Dams is a smaller number. It's not close to 85%. But what that means is that if we're going to talk about fixing problems on dams and levees, we also have to keep in mind who's going to pay for it and who's going to make the decision. So we're not going to go into any more detail on those aspects right now, but they're things to think about. All right, so what are some potential failure mechanisms for embankment dams? So you can have internal erosion or through seepage. You can have under seepage. You can have overtopping. You can have erosion, generally that relates from the overtopping, but not always. You can have structural failures. You can have saturation or breaches. And we're going to generally cover most of these. So here is another cartoon from Canada's BC Ministry of Forests that shows a cartoon of a dam and shows some of the places where we can have failure mechanisms. We can have trees growing on a dam that eventually compromise its structural integrity. We can have slumps. We can have cracks that form. We can have failures in the concrete, although this talk is not focusing on concrete issues. We can have settlement, again, cracks, animal burrows, seepage. We can have wear on the surface from erosion that doesn't have to be from overtopping. It can be from a heavy rain, all right? So again, here's another cartoon that shows sort of the same things, but zoomed in a little bit more of what are some of the failure mechanisms that can occur on a dam. And then as we move further, we'll talk about some of the methods that can be used to detect these and allow for remediation. All right, so these are just some images of spectacular dam failures. And just to get an idea of what the worst case scenario is if we don't do maintenance, upkeep, and apply geophysical methods to them. And some of these are pretty spectacular. All right, so here is an example of internal erosion, which is a large problem for dams in the sense that as we have moisture going through the dam and into the core, sometimes a flow path can occur through the dam. And what happens is once a flow path forms, eventually we get water coming out on the downstream side. And as that water is coming out, it generally starts to carry material with it. Typically, we're worried most about the materials that are on the surface of the dam. And then eventually we can have some clay from the core getting through. And what will happen is as enough material moves through, that flow path can increase in size such that a failure can occur on the dam. So here's a picture that shows under seepage as well as through seepage. And the main difference is that the under seepage doesn't necessarily have to go through the core. For example, if there was a location where the core of the dam didn't actually touch bedrock or some other impermeable medium below the dam, you could have under seepage there and it wouldn't go through the core. Whereas if it's through the main portion of the dam, then it most likely would go through the core. And then overtopping, here we have a picture on the left that's just a cartoon of what the original dam profile was in the dashed line, the water flow, and then what the dam profile is now as the overtopping has removed a significant portion of the material comprising the dam, and then a picture on the right of what that may look like in reality. So now we're going to go through geophysical methods that are applicable to assessing issues with embankment dams. And these are the ones that you're most likely to come across. There may be some that you have seen someone use that we aren't covering here. If you have questions about those, bring them up at the end, but we tried to cover the most common approaches. So we've broken these down into electrical methods here. So that's spontaneous potential, SP, electrical resistivity tomography, and Masw. Then electromagnetic methods, ground penetrating radar, frequency domain electromagnetic induction, time domain electromagnetic induction, seismic methods, seismic refraction tomography, multi-channel analysis of surface waves, downhole seismic, crosshole seismic, and then other methods. And temperature monitoring, surveying of the top of the dam using global navigation survey systems, and then interferometric synthetic aperture radar, INSAR, is get a brief mention here, which technically should be in the electromagnetic section, but I decided to put it here since it's less common and slightly different. All right, so let's go into a little bit of detail on each method that we talked about. We have a couple of slides on each method. This is not intended to be a full course on each method. We have some other webinars that go into much more detail on each one of these methods and can provide you more information on any of them afterwards. So what is spontaneous potential? It's also known as streaming potential. It's a passive technique. It measures naturally occurring electrical potentials in the ground. It is the only geophysical technique that we're going to talk about that responds directly to fluid flow. Because water flowing through the pore space of the soil, it generates an electrical current. And that is an electrokinetic phenomenon. So we can measure a voltage that is induced by that flowing water between pairs of non-polarizing electrodes. And SP anomalies are on the order of tens of millivolts. Those are usually related to seepage. So here's a couple pictures from Zong's website showing a series of SP profiles performed along a embankment dam. And you can see the dotted lines indicate where the measurements were taken. And then the gridded colors indicate SP anomalies. So SP is a very powerful tool. It's a very inexpensive tool in that you can make these measurements for a total cost of hundreds of dollars. A pair of non-polarizing electrodes, a high quality voltmeter, and some cable. But it's also difficult to interpret. And there has been a fair amount of work in this area on interpretation, but a lot of it is like we're seeing here, is just plotting and gridding and looking for anomalies and in potential seepage areas. Megan Sheffer, who did her PhD at University of British Columbia, has done a lot of work in this area. So the next method that is very applicable to embankment dams is electrical resistivity tomography. And with ERT, we inject current between pairs of galvanically coupled electrodes. That means two metal rods that are pounded into the ground. We measure the voltage between multiple pairs of galvanically coupled electrodes, depending on the system you're using. That could be anywhere from one pair up to usually 8 to 12 is sort of the maximum number of pairs you would use for the voltage measurements. We calculate the resistance from these currents and voltages. We plot the resistivity at center points to create what's called a pseudo section, and then we can invert that resistivity data to create a subsurface resistivity model. Now, here's a sketch of a resistivity setup just using 4 electrodes, 2 current electrodes, 2 voltage. And it's just to indicate that for electrical resistivity tomography, how we calculate the resistivity is a function of the array. And the array is just the geometric description of where the electrodes are located relative to each other. And for each array, there's a geometric factor. And I also use this one to indicate that most resistivity surveys done for embankment dams are profile 2D, but resistivity is always a 3D phenomenon. And Why would we want to use resistivity as a very powerful method here? It's that the difference between dry, wet, fully saturated soils is very apparent in electrical resistivity data. And typically what we're looking for when we're trying to assess subsurface conditions at a dam is anomalous moisture conditions. And so it's a very powerful technique. So what are the types of surveys that can be used? A 1D sounding is the simplest one, but that's not something that is almost ever done in today's environment on a dam, because we have 2D electrically switching systems for ERT, which is a line of electrodes where we can place a number of electrodes into the ground along a profile. We can choose the spacing between the electrodes, we can choose the array, and then the instruments will automatically switch based on what we've programmed them to do, where the current and voltage locations are, so that we can image the subsurface effectively and much faster than we used to be able to do manually. Now, it is also possible to do a three-dimensional electrical resistivity survey, but they aren't done a lot. And the reason for that is that it's quite often sufficient to do a pseudo 3D survey, which is just a series of parallel lines where the spacing between the lines is relatively small. And that's a subjective word that can be talked about later. And that's a 2.5D. And you can do a true 3D survey where you have electrodes distributed over a surface and do multiple source and receiver locations. But this is typically much slower than doing a 2.5D pseudo 3D survey. And so it's usually only done more in research settings. But for dams and levees, actually one of the most powerful approaches that can be taken is a time-lapse 4D resistivity survey. And it can be any of the previous types, 1D, 2D, 3D. It's just repeating the exact same survey at the same location over a period of time. And so I've worked on a number of projects in the past where we were worried about anomalous seepage, and that seepage was a function of the season. These were mainly focused on levees, and when the water level in the river is low, there's going to be a small amount of seepage. And when the water rises up and gets towards flood stage, there's a much higher head difference between the wet side and the dry side. So the seepage increases. So what we would do is we would permanently in place arrays of electrodes, and you can either then go out with your instrument, connect it, and do your measurement on a regular interval or an interval related to water levels, or you can leave an instrument out there, as in many of them can be remotely controlled and set to collect on a regular schedule. So here's an example plotting both SP and resistivity. And the reason that we plot both of these is if you want to do a true quantitative analysis of SP data, it really requires knowing what the subsurface resistivity distribution is. But even if you aren't doing a quantitative SP analysis, you're just doing qualitative like we are here, where we're plotting the SP responses versus distance along the line, we can see how those correlate with subsurface anomalies in the resistivity data. And you can also collect both of these surveys with the same electrical resistivity tomography instruments. Some of the instruments allow you to have both of them connected at the same time and it automatically switches. Others, you just lay everything out, do one survey, and then disconnect from one type of electrode and connect to the other. But here we can see some potential seepage zones. All right, so Masw is a method you may have heard of less often, but it's actually can be very powerful for seepage studies because a current electrode is placed in the source body of water. Another current electrode is placed downstream where we think the seepage is occurring. If we can see a seep occurring, we would definitely put it there. And then we move voltage electrode pairs over a profile that is across the face of the dam, typically perpendicular to what the expected flow path is. And we're just measuring the voltage potential between these pairs. And then we can change the spacing, but sometimes that's not even necessary. We can get a voltage anomaly similar to what we would see in SP, but it should be a stronger anomaly because we're inducing a current flow, which should be larger in scale than the naturally occurring SP anomaly. Here's a sketch of what I was describing for Masw. We can see the upstream side on the dam where there is water and a current electrode is inserted there. And then downstream, there's a current return electrodes. And then on the bench of the downstream side, you see a pair of voltage electrodes, and those would move along the that bench there in a long profile to look for an induced anomaly. All right, ground penetrating radar is a fast method. There's been a huge amount of improvement, but basically we have a transmitter, a receiver, we generate a high frequency radio wave. It propagates away from the transmitter through the subsurface. It interacts with changes in electromagnetic properties in the subsurface, and we measure the response of the reflected signal. And so GPR is a really powerful technique, but it is very site dependent in its performance. And typically at dams, it doesn't work that well just because the goal of the core of the dam is for it to be a clay, which is impermeable, and a semi-permeable material on the surface. And what that means is that we end up with a relatively highly attenuating surface for GPR. So I have this one picture here showing an example GPR section across the downstream side of a dam and an area marked as a potential seepage zone. But if you look on the far right, what the depth range is here, that's like 2 meters, right? So that's not very deep relative to what we're usually interested in for issues on a dam for detecting anomalous seepage. So frequency domain electromagnetic induction is a very powerful tool. It's an active EN method, a continuous sine wave source generated in the transmitter, and then a received signal in the receiver that's a combination of that source and the induced response in the subsurface. It is used for site reconnaissance, and it gives great lateral resolution. And the lines can be thousands of feet long. You can do grids. Here's a picture of me walking across a dam face doing a number of parallel profiles. And essentially what you have is you have a transmitter and receiver separated by a distance. And the idea is that they operate in the low induction number range. And that means that the geometry of the instrument controls the depth of penetration. And we are just looking for anomalous conductivity in the subsurface, which would typically be areas where there is soil that is wetter than other areas. Time domain electromagnetic induction is similar to frequency domain electromagnetic induction. There's typically 2 or more loops, one for transmitting, one for receiving. There may be multiples for transmitting, maybe multiples for receiving. Traditionally, the system is stationary and a sounding is performed, and then it's moved to the next locations, and multiple soundings can become combined into cross sections. I think this picture here is of a Zong system on the Trinity River levee in Dallas doing a sounding. And here's a cartoon of what happens. Here it's showing that you have a large transmitter loop, a small receiver coil, the transmitter and receiver electronics, and that the transmitter loop generates a signal by turning on, turning off, turning on, turning off, and the electromagnetic wave propagates away from that transmitter loop in what some people call smoke rings. They're increasing in size as they go down in depth, and secondary electromagnetic fields are generated as they interact with changes in subsurface electromagnetic properties. Now, there's actually been some improvements in the last few years in time domain instrumentation, and now there are mobile time domain systems available. And this is a picture of us testing out the system we just got that allows us to do what I showed you a couple slides ago in terms of point measurements with time domain, but moving. So what this essentially is that the horizontal large loop there is the transmitter, and then the cylindrical object is a housing that holds 3 perpendicular receiver coils. And with this system, we can actually collect a significant amount of data per day moving soundings. Essentially, we're making a sounding every meter as we move along the ground with lots of stacking, and we can get imaging down to about 25 meters. And here's some sample data of a profile there on the left, and then a map on the right. So this is actually a really powerful screening tool if you're interested in deeper depths than you can easily get with frequency domain instruments. So now we're going to talk about seismic methods. So why would we use seismic methods on dams? Well, the main reasons are mapping bedrock depth, detecting voids, mapping subsurface geology, and then calculating seismic site classification. So this is seismic refraction tomography. Typically, you put energy into the ground. That's what the picture is on the person on the right with a sledgehammer hitting a metal plate. That triggers the seismograph to start recording. And then we have an array of geophones that are connected to the seismograph. And as the seismic energy interacts with boundaries in the subsurface, where there is a velocity change, energy is returned to the surface, and we measure that. And so from this, we will record the signal of the geophones. We will pick the first arrivals on each trace, and we can calculate a subsurface velocity model. And we can do refraction tomography for both shear waves and compressive P waves. We have a couple of webinars that cover this topic in more detail if you'd like to learn more. Here's an example of just mapping the subsurface geology with refraction tomography. And see, we did here a correction for the location of all the sources and receivers for elevation. And then we're selecting the unsaturated alluvium from the saturated alluvium and the bedrock based on velocities. All right, so another method that's applied here is multi-channel analysis of surface waves. Again, it's the same equipment as seismic refraction tomography, the same data collection. The picture I showed here is actually from a land streamer system, which is just a faster way to collect data instead of emplacing geophones at fixed locations. They're all attached to a heavy weighted device that allows you to move them along the ground, and a picture of an active seismic source, which we use on many of our surveys. Here, though, we after we've recorded all the data, we convert the data to the frequency domain, pick a dispersion curve, and calculate velocity versus depth. We typically do both seismic refraction tomography and MASW at the same time. There are minor differences in the setup for collection, but since they're really minor, we often do both and end up processing the data sets both ways. Oh, and there's a picture of a dispersion curve, which is the velocity, the phase velocity versus frequency. And then here's a picture of an MASW profile across the creek. And again, we've got the ground surface. We can see loose saturated sand, dense saturated sand, and a hard shale below it. And we can see where our velocities are there. And then over on the right, we have a borehole that we use to ensure that our interpretations aligned with other data that was available. So crosshole seismic is a method of putting a source in one hole and a receiver in another hole. And we can use this to get velocities between the holes. And we can also use, so we can use this for imaging the subsurface to get a velocity model. We can use this for looking for voids between the holes. But most often this survey is done as a way to get seismic site classification, which we can also get from refraction and MASW surveys. And the seismic site classification is a way to determine what the probability of failure is, essentially from an earthquake at that site. And we have a webinar specifically on seismic site classification if you'd like to learn more. So as I said, you only need one borehole for transmit and one for receive, but the ASTM standards suggest using 3 in a triplet because you have a little bit more redundancy in your data. And we can calculate other properties from this. We can get Poisson's ratios as well as shear and Young's moduli. A downhole seismic survey is similar to a crosshole seismic survey, but we only require one hole. And we have a source on the surface, and we have a receiver that we move down the borehole and take measurements at fixed depths, typically somewhere on the order of 5 to 10 foot intervals. And we usually use 2 3-component geophones that are separated by 5 feet, and we move them down the hole. And then we have a trigger on the surface. And so from this, we can get velocity versus depth, and we can get P wave and S wave. It's simpler than crosshole, and it only requires 1 hole. So which one you select really depends on the specific problem you have at your site. All right, here's an example of doing I believe this is actually a downhole seismic survey that was done by some of our staff. And what we have over here is a plot of velocity versus depth. And we are plotting both P wave and S wave velocity. All right, temperature monitoring is a method that's also pretty powerful for looking for issues on earthen embankment dams. And we're looking at the difference between the bulk temperature of the dam structure itself versus the variation in temperature that could be caused by seepage coming through the dam. The expectation being that there is a temperature differential between the water that's impounded in the reservoir of the dam and the dam structure itself. And the ways that we can measure this, there's a couple of different ways. We're looking for high variation in temperature, but we can do this either with temperature sensors that are on the surface or down in holes to look at temperature variations. We can use optical fiber sensors, which are basically long strings of fiber optic, which can be placed in the dam. And those can be used to determine temperature variations because the temperature variations are going to change the optical wave propagation down the fiber. And these can essentially, you can turn a section of fiber optic into a sensor, maybe a meter long section, and then you can just move 1 meter at a time as you look along the length of the fiber. And you can also do temperature monitoring with FLIR cameras, so an infrared camera. So if there is seepage coming out of the downstream face, you can do a remote assessment of that, and you can see by the temperature difference that seepage is occurring, but maybe it was difficult to see just visually. So here's a picture. On the right is just a FLIR camera picture, probably from an unmanned aerial system or drone, where we can see a seep occurring on the face of the dam that's at a different temperature than everything else around it. Whereas on the left, there's a sketch of how we would bury fiber optic cables in the dam upstream and downstream, and we can use those to determine temperature distributions and changes and indicate where seepage may be occurring. All right, so now we're going to talk a little bit about Global Navigation Survey System, of which the Global Positioning System, GPS, which is what most people would call it, is a subset. GNSS just means all of the constellations that are in orbit from the different countries. So the European Union, Russia, the United States, Japan, China. This is just a way we can go out and measure elevations, and we can look for places where there are low spots. And there are 2 types of low spots that we'd be interested in. One where the dam height is not actually at the design it should be, but this is something that probably shouldn't be an issue. The other is looking for elevation changes that can indicate subsidence. Depending on how you make these measurements, they can be very accurate, sub-millimeter, well, sub-centimeter in the millimeter range, depending on how much time you want to commit to the effort. And some people might argue that this isn't really geophysics, but it's all related. Another method is interferometric synthetic aperture radar, INSAR. And we can use this data to indicate surface changes. So either elevation changes across the top of the dam or surface changes along the face of the dam. and these can indicate potential for failure. And so we can look not only at the elevation change, but we can look at how fast that is occurring if we have a sensor in place. And so on the left at the bottom there, there's a system that we have, the IDS IBIS system, which can be used for monitoring surfaces, dams, spillways, mines, whatever. And this would be put in place, and it would collect data on basically an hourly interval to monitor a place that that we think has potential for failure. Whereas on the right is a picture that's actually satellite based in SAR and looking for subsidence issues that occurred there. All right, so now we're going to go through one of our case studies. This is a project I did a few years ago on Benbrook Dam in Fort Worth, Texas. There was standing water seen at several locations after significant rainfalls in 2015, and there was indications of some seepage, so we performed some field work there. On the left is just a plot of Benbrook Lake relative to Fort Worth, Texas. And on the right is a zoom in on the dam structure and some areas of interest. So we've zoomed in a little bit more on that figure from the right, and we tried to cover as much of this as possible in a little over a week of data collection. So what did we do there? We did a number of methods. The main focus was electrical resistivity tomography. And then we also did electrical conductivity profiling, or frequency domain EM, FDEM, ground penetrating radar, and then we did a number of GNSS measurements, both to locate all of our measurements and to understand the elevations. One of the reasons that we use multiple methods here is because it's almost always better for geophysical site assessments to use at least two methods, because if two methods indicate that you found the target of interest, that's a positive. If one does, maybe you can explain why the other one does, but if you don't see what you're looking for with either of them, there's a low probability that it's there, but you can't prove a negative. So it may still be there. So the reasons we did the EM and radar surveys were that typically with switching resistivity tomography systems, once you've set everything up, you have a period of time between each survey section where you don't have to do anything. The system is just collecting data, which is nice after 2 hours of carrying heavy things around and pounding things into the ground to take a short break, but then you can use some of that time to collect additional data. So here are two plots of the apparent conductivity measured with the Geonyx EM31 frequency domain electromagnetic induction instrument seen previously. The one on the left is a large scale survey where we did, I don't remember how many lines, I think it was 10 or 15 lines across the toe of the dam. And then on the right, that area is zoomed in, which is what is this small white box over here on the left figure. And the anomalous areas actually correlated very well with both the standing water that was observed there during several heavy rain events, and also with all of the buried utilities that actually are in the dam. So I was really surprised with how useful this was. And had I thought about this earlier in the trip, I would have probably collected a lot more data with it, but I didn't start it till the end of the trip. So here's an example of 3 parallel resistivity tomography profiles that we collected on this dam. I'm going to go back one slide. So these are all aligned essentially with this grid on the right. The first one is at the toe, and the other 2 are moving up the downstream slope. And so I tried to align them. They're not all the same length. There's this one vertical blue line here that I said there's a buried conduit running up and down. And it looks like we're getting pretty good data, in some cases down to almost 100 feet, maybe even 100 feet in some cases. And there are some areas that are anomalous that also align with where there was standing water in the previous couple of years prior to this, which is the area bounded by the box on the left side of the figure. And that is also aligned with where the original channel of the of the river occurred. So our second case study area is Old Timbers Dam at Jefferson Proving Ground in Indiana. It's just north of Madison, Indiana, and southern Indiana. It is now called the Big Oaks National Wildlife Refuge. And we were asked to come look at this because there was a seepage problem at the toe of the dam, which you can see in the bottom right where that weir is, that there was water flowing out at several gallons per minute. So we know water is flowing under the dam. The question was, where is that water coming from? Is it coming from the dam, or is it coming from an underground aquifer? And part of the reason this is an interesting dam is this dam was built as a hobby project by employees of the facility so that they would have a place to go fishing on the weekends. I can't remember exactly the year, but about early 1900s. And so this entire dam was built as a hobby project by employees. So what did we decide to do there to better understand this? So we did electrical resistivity tomography, we did Masw, which I discussed earlier, and we did electrical conductivity profiling, and we also did geochemical analysis and GPS, GNSS measurements. And here's some pictures of us performing these surveys. In the top right, there's two pictures of where we did the Masw, which is putting one electrode in the reservoir behind the dam, putting one electrode at the bottom of the dam where the outflow seep was occurring. Then the bottom left shows the electrical resistivity tomography surveys, which went all the way across the dam. And on the downstream, left side downstream, it actually went out into the woods there, and that part was not mowed and maintained. And that was an unusual field experience where I managed to cut all of our tape measures with machetes in the course of 2 hours. It was a little frustrating. Then on the right side is me carrying the Geonyx EM31 to do conductivity measurements. So here is a plot of both one resistivity line as well as the Masw measurements that we made along that same line. And we do see a few places where there's an anomaly in the Masw data. And there are some anomalies that also occur as subsurface fractures along the bedrock. So those are probably related. So let's look at this line here. Oh, let's see where our seep is. Well, we can see our seep marked here on the electrical resistivity tomography data. And above that, we actually see a anomaly in the Masw data, which is positive. That's what's supposed to happen. And then here is summarizing all of our data with elevation corrections and looking at the EM31 data, the Masw data, and the ERT data all plotted on the same lines. And we can see that there are anomalies actually in all of the data at the same place. And so that was positive. That was showing that there was a connection. And then what we also did there was we did some geochemical analysis of the water in the lake and the water at the seep. And that indicated that, yes, the seep was coming from the reservoir itself. And then here are some interpretations that we made showing our locations of our flow path for Masw, where our resistivity lines were, where some of the GPS measurements were made, where the heavy seepage was occurring, and those were combined with our interpretations. And then here's a plot of our EM31 conductivity data. And we can see some interesting anomalies in there, but it's not super indicative of where the seep may be, but that was probably because the seep was relatively deep across several of these lines, and also that where the seep went on the left side downstream, there was lots of trees. It was actually into the forest. And the topography there was not smooth. It was not like the main face of the dam, which is the regularly mowed and maintained section. And so we ended up where our height of our instrument above the ground was changing every few steps and made it very difficult to get good data to interpret there. All right, so to summarize this presentation, there are a number of geophysical methods that are applicable to studies of earthen embankment dams. Which method you select depends on the type of failure mechanism that you're worried about. If you are worried about seepage issues, then you're probably going to pick an electrical or an electromagnetic method. If you're worried about scour or slumping or other large scale issues like that, then a combination of GPS or GNSS or INSAR, other methods like that, or even flying over with doing photogrammetry, which I didn't mention in this presentation. There are other methods that can be used to assess those reasonably quickly. I suggest that for any location where you think there is a seepage problem, that electromagnetic survey of the dam is probably the first and fastest thing you can do to get some additional information. Depending on your depth of interest, a Geonyx EM31 frequency domain instrument or an equivalent from other companies like Geosensors or Dual EM, some of which even have multiple spacings to allow you to get an idea of the depth that an anomaly is occurring, are good ways to get data down to about 20 feet. Time domain is generally a better way to go down deeper. So like the mobile time domain system that I showed earlier is actually a great screening tool. You can collect data pretty fast. It basically 1 meter spacing in line and 1 meter resolution in depth down to a depth of about 25 meters. If you have more questions about any of these methods, how to perform the work, just what method you should choose, if you need help with doing this work, let us know. Thank you for listening to this webinar. I hope I covered it in an appropriate level of detail. But as I said, we have some other discussions and webinars on some of these topics in much more detail, or we can answer your questions directly. So I'm going to open it up to questions now, and I will switch out of this view and back to letting you see me, and Sterling will curate the questions. So thank you for listening to this portion.
Yeah, so we have several questions. Can you hear me, Ryan?
I can hear you. I'm playing with turning things on and off. All right, you can see me now. All right.
Yes.
Let me turn my volume up a little bit. All right, go ahead with questions.
Okay, so the first question is, what methods can be used across and under a water surface?
If you mean across and under the water surface, I assume you mean on the upstream side. There are a number of methods that can be used. It really depends on if you're worried just about the surface or the subsurface and how deep. So you can do bathymetry surveys with electrical resistivity, and basically the electrodes are floating on the surface, and we're pulled around with a boat, and we can use that to image down to a certain depth. It's not quite as flexible as a surface resistivity survey because we can't change the spacing between the electrodes as easily as we can on a surface survey. So if we have a depth range, we can have a custom cable made to do that to get the range of interest covered. You can do EM surveys that way. Occasionally those are done. And then I've done lots of GPR bathymetry surveys where I'm pulling my GPR system around a lake surface in a little rubber boat behind my boat, and using that to image both the water soil interface at the bottom of the lake as well as below that. It just depends on the electromagnetic properties on how deep you can see. So I don't know, hopefully that answered the question.
Okay, so the second question is, what sequence of investigations do you generally recommend when combining geophysical surveys with geotechnical drilling, or CPT?
So this is a question that's always fun to talk about with the head of the drilling group, because their first goal is to drill lots of holes and keep their guys busy drilling holes. And I actually had a project where we looked at this in my previous job. And what we were doing was we actually modified our CPT truck so that the first section of downhole rod had a electrode on it. And what we were doing was we were trying to leapfrog back and forth of doing a resistivity survey, and then from the interpretation of that first section, choosing where to start doing a CPT push. And then we looked at doing additional resistivity surveys at different depths of the CPT push. What we eventually concluded was that we didn't need to do additional depths, that the maximum depth that we went to for the CPT push gave us another current electrode at depth, so that could improve the subsurface resolution. But the general takeaway from that project was that the time required to do both of those simultaneously made both of them a little less efficient than on their own. So my suggestion is always to do a geophysical screening survey first, then do CPT. And then if the CPT results confirm our geophysical survey, that's great. If they open up some more questions, maybe do an additional survey in an area where one or more of the pushes may have put some questions around our geophysical results. And so again, my ideal approach now is I would go out and do a mobile time domain EM survey to cover as much area as possible and indicate the areas of interest. Then I would go back with the CPT survey and do a number of pushes in the areas where we expect a defect of some kind, or subsurface flow, anything that could be of interest. And then if we want to refine in any of those areas, I would probably then do a resistivity survey as the last approach, but just focused on the areas where we need to refine our understanding.
Okay, so the next question is, how is the MASW field data, shear wave velocity of soil profiles, going to vary as the water table changes?
Well, the MASW shouldn't really have much change with the water table because shear waves don't propagate through a liquid. But you can see changes in the subsurface if there's a compaction difference, a density difference that occurs there. So you can't image through water, but you'll get a slight velocity difference if it's saturated or unsaturated.
Okay. Is there any specific method for sinkhole investigation?
I guess the question is what do you mean for sinkhole investigation, right? So the first question is, are we just trying to define the extent of the sinkhole and the depth of it? Or are we trying to then look for the source? I mean, so those are not the same thing, but they can be connected. So the first question is usually just defining the extent of it. And that can be done typically with different surveying methods, photogrammetry or ground-based robotic total stations or GPS. And then as we want to define the source of a sinkhole, it depends where it occurs. Did it occur on the face of the dam, at the toe of the dam? But again, EM or electrical resistivity tomography are both very common methods for defining the extent of the sinkhole and then seeing if it may extend further from the visible area.
Okay, next question is, are there any issues with powerhouse or other interference with SP?
The answer is yes. Those can occur. Generally, we try to figure out where all of the voltage sources are. And if there's something that can be turned off when we're doing those types of measurements, we ask if it can be turned off. We've seen some data that's caused from powerhouses before. So it's something you have to deal with on the site. And I don't have a great answer of yes, it will mess up your data, or no, it won't mess up your data. It's very site dependent on geometry.
Which of the seismic geophysical methods are most suitable, accurate to get the soil profile?
So generally, I'm not necessarily going to answer it for accurate. It's just a function of what is the soil profile. we would almost always want to just use a surface method. If we can use a surface method, because it's usually faster, and faster in the sense that you don't have to put in a borehole or multiple boreholes if they don't already exist. If boreholes already exist, go do the borehole method. That'll be the fastest in the field, a few hours probably, and the interpretation is relatively easy. If boreholes don't exist, then we have to figure out which method we're going to use. So when I've written proposals to do this in the past, I almost always start with a surface method and put a big caveat that there are sites where the velocity distribution of the subsurface and essentially the attenuation make it impossible to get good data down to 100 feet. And if we say that our results indicate that we're not getting good data down to 100 feet, that you will want to do a borehole method as a follow-up, because we can't answer the question from the data we have. So I don't know if that necessarily answers the question, but that's sort of the approach that I would take.
Okay, next question is, which methods do you recommend for investigating highway and railroad embankments?
So for the highway ones, you can use any of the methods we discussed here. It really just depends on the specific targets. For the railroad, I guess I have to determine how far are we away from the tracks themselves. Are we talking about including the ballast as part of the assessment area, or are we 40, 50 feet away from there where it is soil? And if it's soil, then we can do the same methods here. But for ballasts, we're not going to get great coupling from a lot of the methods here into the ballast itself. And the EM methods generally won't work because you've got a long conductor in each of the rails. And so it will couple to that. So the answer is it depends. I'd have to know more about the specific situation.
How does MALM compare with willow stick?
So conceptually, they're similar. So the idea behind willow stick is that you put a current electrode in the source reservoir, and you put one downstream where you think the seep is occurring. But instead of making a voltage measurement, you're using a magnetometer, and you're measuring the induced magnetic field caused by moving electrons. So you have a current flowing, and right-hand rule, and you're generating a magnetic field from that, and you can supposedly see the same thing. So at some level, they're similar. Both of them are methods that occasionally work really well and lots of times don't work. So they're not general purpose methods. How about that?
Okay, can ERT detect a piping in progress inside the dam body?
Potentially, yes. It really just depends on how deep it is and the size. We've done some lab scale measurements in the past looking at this, and done some large scale ones over known pipes. And sometimes we can see them and sometimes we can't. Like I said, it's a size of the target versus depth is really what's controlling whether or not you can see it.
Are there any methods for finding shear wave velocity greater than 100-foot depth?
You can do MASW surveys. They can sometimes be deeper than 100 depths, and you can do shear wave refraction tomography. It just depends on the site. It just, for engineering, 100 feet is sort of that magical cutoff. So that's typically what we're targeting. And the requirement for the International Building Code for a VS30 or VS100 is 100-foot depth requirement. So yes, you can image deeper than that. It's just that the systems we typically are using in the field for sources and are optimized for shallower, but we've seen much deeper than that using the MASW or SRT before. It's just site dependent.
Okay, next question is there a specific method you recommend to locate/delineate the dimensions of an underground cavity in limestone?
So the most common combination of methods that would probably be used here is a combination of electrical resistivity tomography and microgravity for looking for limestone, because it's usually a nice contrast in both resistivity and a nice contrast in your gravity anomaly. So that's a pretty common combination for that.
Do you use laboratory analysis to typify soil parameters along with field investigation?
Yes, I have spent a large portion of my career making lab measurements of soil properties for geophysics. The one thing to keep in mind is that it is essentially impossible to exactly reproduce the in situ conditions in the lab. So we end up having to make a lot of measurements over a range of moisture contents, a range of compactions, and a range of sample volumes, because you can get, there's an entire field of mixing theory, effective medium theory, which is if I have an isotropic homogeneous medium and then I start adding materials to it, and they are at different spatial geometries and different sizes, how is that going to affect the bulk measurements? I mean, that's what Archie's law is for understanding what the resistivity of a volume is as a function of the resistivity of the matrix, the saturating fluid, the porosity, the permeability, the tortuosity, and at higher frequencies, there are other mixing models, and just depending on the properties. So yes, I do that. And it gives you good bounds, and it may give you a reasonable central value. They don't always align exactly with the field measurements, as I said, because of trying to reproduce all the other conditions.
Does riprap prevent the use of any of the geophysical methods presented?
Yeah, so riprap makes doing a resistivity tomography or any of the seismic surface surveys really difficult, because you have to be able to couple either your electrodes or your geophones to the medium, and the riprap is typically a giant rock. So is it possible to like couple a geophone to a chunk of rock there and do that? Yeah, but you end up with a weird transition between the bottom of the riprap and the material that the dam itself is composed from. And then you can do a GPR survey across the top, but again, walking across the top of the riprap can be an ankle breaking experience with GPR or EM methods. But the EM methods are probably the best if you're trying to go across the riprap, or if you have a place where we've tried lowering electrodes down, but it doesn't always work that well.
Okay, next question is, have you performed 4D ERT surveys using a conductive tracer, NaCl, to define piping in the dam?
I think that's sodium chloride for salt water. And no, I haven't done that. I'm pretty sure there are some people who have done that. There's a 4D ERT modeling package that exists for interpreting and processing data. I've seen a couple, I think, of these of lab scale ones, but I'd have to go dig through my folder of references. I haven't done any of those.
Are any of these methods cost-effective for putting in a permanent long-term monitoring system?
The most cost-effective ones for long-term monitoring, there's typically three things that I would suggest for that. You can put in a resistivity monitoring system pretty inexpensively with just permanently in placed electrodes, and I've done those. The optical fiber approach can be done pretty effectively in the sense that the fiber itself is actually the cheap part. And in placing, it's not that difficult. And for both of the ones I just mentioned, then the issue is how you want to do the monitoring. So do you want to bring the instrument that connects to the end of that long string out on a regular basis, or do you want it to permanently sit there? Ballpark a resistivity instrument that you would have to do is going to be somewhere in the $50,000 to $100,000 range for the instrument. And I mean, maybe the instrument's a little lower, maybe it's down around 30. Whereas the instrument for the fiber optic monitoring, the prices of those have come down a lot. The ones that we used to use in my previous job started at a little over $1 million a piece. And I think they're down to a few $100,000 a piece now. So they're not necessarily ones that people are going to leave there permanently, but you might be able to bring them back out. And if you think you're having a subsidence problem, probably the easiest thing for long-term monitoring is you can put fixed reflectors on the dam, and you can just put a robotic total station at an appropriate location, and you can have it automatically scan all the reflector locations on whatever interval you want to look for changes in elevation. Those are probably the three methods that you can do long-term monitoring that are not prohibitively expensive.
Okay, the next question is, I noticed that you didn't mention gravity methods here. Are gravity methods at all effective for the assessment of embankment dams?
There are applications where gravity can be very useful. If you're looking for a large void, if you're trying to better understand the depth to bedrock and density distributions, it's just that geophysical methods can be rated by one, how effective they are to solve your problem, and then two, how long they take to do the measurements and interpret the data. And gravity is pretty slow. So I occasionally do gravity surveys, but it's not at the top of the list of what people are typically going to use for embankment dams. Yeah, there's some applications, but it's not in the short list of things that are usually used.
Okay, this looks to be the last question. Have you considered using a GPR off a drone platform for difficult terrain such as riprap or heavy brush?
No. So some of the reasons for that are in the US, you have to deal with several issues there. One is the Federal Aviation Administration, the FAA, and the other is the Federal Communications Commission, the FCC. So generally in the US, you're not allowed to have a radar antenna flying. There are some exceptions to that, but generally, if you're going to have an antenna above the ground, so an air-coupled system, it has to be below 1 meter above the ground. And so there are lots of logistical issues there. I'm a Part 107 pilot. I do drone flights all the time with infrared, hyperspectral, multispectral, LiDAR, photogrammetry, all those methods. But I haven't tried with the radar just because of the legal issues we have to deal with. Other countries have different rules than the US, so it may be applicable there. But generally, if you air-coupled antennas are a poorer choice than ground-coupled antennas because a significant amount of the energy is lost in the reflection between the air and the surface. And so I only use air-coupled horns for some highway surveys and occasionally like a railroad survey, and almost everything else is ground-coupled.
Okay, that's all the questions.
Well, I would like to thank everyone for coming to this webinar and asking lots of questions. You should all have my email address if you have specific questions that weren't addressed here. And as Sterling just posted, we are recording this and we will be posting it online after it's been cleaned up a little bit. And again, thank you.